the geometry of line correspondences in 3D image reconstruction, the line multiview variety. So please, Angélica, the stage is yours.
Thank you, Lucas. So let me share my screen. Yeah, so thank you for having me, and thank everyone for joining this session. So yeah, as Lucas was saying, I am gonna tell you today a little bit about some project in computer vision, where algebraic geometry kind of helps us understand how to reconstruct images, or yeah, how to create models of an object or a scene, starting just with pictures. So this is the, let's say, the 3D image reconstruction problem. As I was saying, you start with a bunch of pictures, and what you want is to create a model, a 3D model of whatever it is that you're taking pictures of. So this camera model, this 3D model has like two components. One is the cameras and the position of the cameras, and the other component is the actual object. So the position of 3D points or 3D lines or whatever it is that you actually want to reconstruct. So normally the 3D reconstruction is done in following the pipeline that I'm gonna show you now. So first you start with just a bunch of input images, that is your data. And then what you do is that you start taking maybe a couple, 2 images or 3 images, and then you start identifying common features of these images. So in this particular image that I have here, this algorithm was identifying just common points. So these common points are just points in the pictures where you kind of suspect that they come from the same real point, right? And then once you have done that, you forget about the pictures. And then what you are left with is just a bunch of point correspondences, okay? So in this picture here, for example, what you are left with is, let's say, this point, these 5 points here in this picture that have been identified or related to the other 5 points in the other picture. That is what you're left with. And then ideally what you want to do is to use algebraic geometry, algebraic geometry to determine which ones are the 3D points, and also determine the position of the cameras. Okay, and finally you are left with a bunch of with your 3D model once you expand from once you repeat this process with more than 2 images. Okay, so our project falls into this part here. Particularly, our project is about a process that is called triangulation. I will explain it in a moment, but it's just a step here in this third part. So some algebraic questions that can arise in algebra in the 3D reconstruction process. So first is, how much information do you need to effectively estimate the positions of the cameras and the points, right? Because maybe you identify a bunch of data that might be, I don't know, an overload of data that you actually don't need, or maybe you identify too little data and you cannot do the reconstruction. So how do you measure this? What is the smallest amount of data that you need? So this is something that is called minimal problems. So assuming that you have already found your cameras or your camera positions, then how do you decide if a point correspondence is real? I mean, it comes from an actual point or not. So how do you describe all these point correspondences, for example, or all the line correspondences? This is something related to some multiview geometry. The things that I'm writing in parentheses are just maybe terms that you can, if you're interested, you can just Google them, and that is the area that tries to solve these questions. The third part is, for example, if you have a point correspondence now that you have identified, then how do you find the actual 3D point whose picture was taken? That is called triangulation. And finally, what do you do with noisy data? So how difficult it is to remove noise from images. And in this case, something that can help us understand how difficult removing the noise is just the Euclidean distance degree of a variety. So I'm going to focus on these three parts, and I'm just going to mention a little bit of minimal problems that, even though it's not it's not exactly my project, there are people here in KTH working on that. So I'm just going to give a shout out to them. So first, let's try to model this process of taking pictures and try to understand mathematically what does it mean to do the reconstruction. So we are just going to model the process of taking the pictures with a map. And this map is going to take just a set of points or lines, and then a set of cameras, and taking the picture is just applying a function. And then this set here is just the set of all the possible pictures, right? And this map here is called the joint camera map. Now, this definition is a little bit generic, and this map can actually change a lot depending on which camera model you choose and which data you have. If you have a bunch of points, then this set is just a bunch of points. But if you have points or lines, then this set here is going to be points and lines and so on. So both things can change a little bit. So I'm just going to mention two types of cameras. For more camera models, of course, I provide here a reference, camera models and fundamental concepts used in geometric computer vision. There are plenty of them in case you're interested. I'm just gonna mention two. One is pinhole cameras, and the other one is rolling shutter cameras. And the main difference is that the pinhole cameras take the whole picture at the same time, whereas rolling shutter cameras scan the scene, right? So they take just one line at a time, and then the line scans. So there is like a time component when you take the picture. And so if you take a picture of some scene or object that is still with no movement, then the two cameras produce the same image. But if there is movement, then the rolling shutter cameras have some distortion. So I have here a video. Hopefully it will work. Oh no. Yeah, I have a video here. Yes. So the image on top is taken with a pinhole camera, let's say, and the one below is with a rolling shutter camera. And hopefully you will see a distortion, especially in the tail of the helicopter. It will come back in a moment. So if you see the tail, like in the image on top, they look very straight, but in the image below, they look a little bit curvy. So that is the distortion that appears when you're taking your picture with a rolling shutter camera. And you have to take it into account when you're doing the reconstruction. Our project focuses on pinhole cameras, okay? And the way that we define a pinhole camera mathematically is just with a matrix. So a pinhole camera is just going to be a matrix of size 3 by 4 that has full rank. And the process of taking the picture is just doing a projection from P3 to P2 with matrix multiplication, and that's it, right? So you have a point and you just project it onto your camera here. This map is defined everywhere except in the kernel of the matrix, which we call the center of the camera, which is the only point that the camera cannot take the picture of, right? For a formal definition of rolling shutter cameras, you can go here to this reference. You can see different types of rolling shutter cameras that have this time dependence that I was mentioning before. Okay, so now that we know what a camera is, or at least what a pinhole camera is, right? We should go to the next step, which is try to understand how do we filter the information that we need to do the reconstruction, right? So remember that I had mentioned before that we might identify a bunch of data, but we wanted maybe to know how, what is the minimal amount of data we need to do an effective reconstruction. And here's where minimal problems come into play, because the idea is that a minimal problem is a reconstruction problem where the joint camera map has a finite fiber. So for a generic point in the image, in the image of the joint camera map, the pre-image is, let's say, finite. I am skipping some technicalities here, but that is the main idea. So Here, for example, there is a classic minimal problem, which is 5 points seen by 2 pinhole cameras. In that case, the joint camera map is this, right? So you have your 5 points in P3, you have your 2 cameras, and then this goes to P2 times P2, and then generically, the pre-image of this, the fiber of this map, the fibers of this map are finite. Whereas here, for example, if you just have 2 points or 1 point with 1 camera, this is clearly not a minimal problem, because all the points that are like, if you take the picture of a point, all the points that are behind or in front have the same image. So the pre-image of this is not going, the fibers of this is not going to be finite. This is a very silly example, but that is the idea. The idea is that in a minimal problem, you have a finite options for both cameras and objects in the real space. So the reason why I'm bringing this up is because here's where I'm going to give a shout out to some other people here in KTH, because Kathleen Kohn here, together with Timothy Dobbs and Anton Leikin and Thomas Paitla, they gave a complete classification of all the minimal problems for calibrated pinhole cameras, assuming that all the cameras can see all the objects, right? And this is these are results that are accomplished with algebraic geometry, and it's very nice. And also on top of that, Orlando Marigliano right now has an ongoing project trying to detect minimal problems with the other camera model, with rolling shutter cameras. So just a shout out to both of them, because they are also working in computer vision. Okay, so the good thing about these minimal problems is that they tell you, as I was saying, the minimal amount of data that you need to do, let's say, an effective or an effective reconstruction. And the main thing that you get from them is an estimation of the cameras, right? So once you have fixed the cameras, and you know the relative position of the cameras, how do you understand, or how do you decide if whatever point correspondence that you got is actually a true point correspondence coming from an actual 3D point? So in order to do that, what we do is that we restrict the joint camera map to some fixed set of cameras, right? So this is what we're doing here. So if I fix my camera set, then I can define this new map, which is just the restriction of the joint camera map to this specific set of cameras, okay? And then the image of this map gives us all the possible pictures of a point, right, with the cameras that you fixed. And then we can define the line multiview variety as the Zariski closure of the image. And the good thing here is that if you have the Zariski closure, then it's nice because you can define this set with, you can describe this set with polynomials. Now, this set, for when we are talking about point correspondences, this set has been studied quite a lot, and is actually well understood for pinhole cameras. I'm just mentioning some of the main results here. So for example, a Grobner basis for the ideal is actually known, which is pretty nice. Also, its ED degree is known, and its singular locus is known for cameras in general position. So this is very nice because it's very well studied. However, this variety only studies point correspondences. But for example, if we go back here to the minimal problems, we see that not all the minimal problems are about points, right? I have some minimal problems here that also involve lines. And this map here really doesn't tell me anything about lines, right? So what can we do with the lines? So what we did in our project was to study the line correspondences. So this is just a very similar definition to the multiview variety, but we are just going to call it the line multiview variety because we are taking pictures of lines. And the idea is that here we are going to consider this map, and it's a map that goes from the Grassmannian 1p3 to the Grassmannian 1p2 p2 m times, right? So just it goes from the set of lines in p3 to m, the set of tuples of the set of m tuples of lines in p2, right? And the idea is that here we take a line and we send that line to its images through the cameras, right? And then we define the line multiview variety as the Zariski closure of the image of this map, okay? So this is the smallest algebraic set containing all the possible images of lines with cameras. And that is precisely what we studied in our project. And there is a manuscript very fresh from our keyboards on archive right now. And this was a joint project with Paul Brading, Felix Riedel, who is also here in KTH, Elima Shehu, and Paul and Elima are in MPI. And basically, we just try to study the main features of this variety. And the main thing was that we wanted to provide a set of defining polynomials for this variety. And we also wanted to study the singular locus. So just so I can tell you what we did, I'm just going to mention something about the notation. And is that the lines in P2, so the elements in the Grassmannian 1P2, they are going to be identified with points in P2. So it's like their orthogonal complement with respect to some inner product. So the idea is that when we think about the map from, this map from lines in P3 to m tuples of lines in P2, we are going to denote that as this lowercase l, and these lowercase l are going to be just points in P2. This is just a notation that simplifies quite a lot the statement of the results and our proofs. And this is the main theorem. So the main theorem is that actually, if your cameras are in general position, then the line multiview variety is just a variety that can be written as the 3x3 minors of a matrix. And the matrix is this one here. So if you see here, this L1 to Lm are points in P2, and this C1 to Cm transpose are the transpose of your camera matrices, okay? So what you have is just here a matrix that collects on a bunch of vectors that are related to the lines, to the points that you started with. So I'm going to explain what this means geometrically in a moment. But the important thing is that in this case, we can define our variety by these 3x3 minors, and the genericity hypothesis in our case is that no four cameras are collinear. Okay. So what is this theorem doing geometrically? So the idea is that if you give me 3 pictures of a line, right? Like if you tell me, if you want to know if this line, and this line correspond to the same, can be reconstructed to the same 3D line, right? Then I can tell you that algebraically by checking these minors of this matrix, right? Or the rank of this matrix. But geometrically, what is happening is that I am going to define a plane, the plane that contains all the possible pre-images of this line. So we call this a back projected plane. The idea is there is a plane that goes through the center of the camera and goes through the picture of the camera. And I am going to do that for all the cameras, right? And if those 3 planes intersect in one line, then we're good, because that intersection is the picture that is the object whose picture was taken, right? So what is happening is that these planes here have as a orthogonal complement, or they are defined, the equation of these planes is given precisely by the columns of this matrix, okay? So that is what is happening here. Now, something else that could happen is that when you, if you do the back projected planes and they don't intersect, then of course these images are not, I mean, these lines in the pictures don't come from an image, right, in the real world. But what can also happen is that if you start with your 3 lines in the pictures, for example, and then you do the back projected planes, and all the back projected planes are the same, what happens here is that you have way too many options for their picture, right? Because any line in this plane could be could give you these images here. And those points whose back projected planes are, let's say, the same plane, they intersect in dimension 2. Those are the singular points of the line multiview variety. So this is precisely the singular locus that appears here. Okay. This, I mean, algebraically, this is just means that the rank, the singular points are the points that are rank efficient, which, I mean, intuitively works. But then geometrically, what this means is that when you do the back projected planes, it turns out that all the back projected planes are the same, and then you end up with a bunch of candidates for images. And yeah, that is the idea. That those are the singular points. So I know that I have like 3 more minutes, so I'm just gonna tell you a little bit what else is in the manuscript that I haven't mentioned here. So I told you that the line multiview variety is a determinantal variety when the cameras are in general position. So what happens when they are not? So what happens when we have more than 4 cameras that are collinear? So we actually studied that case also in the manuscript. And what happens is that in that case, you need more equations than just these 3 by 3 minors, okay? You need more equations. And those equations are related to some intersections of Schubert varieties. So if you like Schubert varieties, you can go and check the manuscript. It's nice. And also, something else that we did is that we did some numerical experiments for the ED degree of the line multiview variety. So we could provide lower bounds for the ED degree for pinhole cameras up to 11 cameras, if I'm not mistaken, if I'm remembering correctly. And then we also studied a little bit the sensitivity of the reconstruction of lines versus the reconstruction of points in terms of if you start with some error in your data, then how that error spreads to your actual reconstruction. Yeah, this was also a numerical experiment. It's also in the manuscript in case you're interested. And now for future projects, what we are doing right now is actually using these computations and trying to understand the ED degree of the line multiview variety. Just a reminder, the point case was already done. We want to get a formula or understand better the ED degree for the line case, which is something that we're doing right now. And also something that would be nice is to get a grammar basis for the idea. That would be nice. That it's, let's say, up there in the air. It would be a nice project to do, in case anyone is very motivated about this. And yeah, that would be it. I have some references, some of the references that I mentioned earlier about the results in the point case. And yeah, that would be it. Thank you so much for listening. If you have any questions, I am, of course, here to answer or redirect you to someone who knows how to be better than me.
All right. Thank you very much, Angélica. So everyone, let's give Angélica an applause in the chat. And thank you very much. So do we have any questions from the audience? I have a question.
Yeah.
So I was wondering what are the difficulties? So apparently having one line and one point are extensively studied. What would you say are the main difficulties for increasing the number of lines or the number of points? So is this somehow easily generalized from studying one point at a time or one line at a time?
What exactly? So
Sorry.
it depends on what you want to do, right? Because
if I want a bit of defining equations, for example, I want 2 lines instead of 1 line. What would you say is the big difficulty?
So the thing is that if you have if you just do 1 line and you have the defining equations for this multiview variety, that allows you to understand if once you have these matching lines, it helps you understand if those matching lines are real or not, right? Mm-hmm. So if you have 2 lines, and you need to understand if they're matching. It depends on what you want to understand, right? Because if you just want to understand that, then just having one line at a time is enough, because then you can apply that first to the first line and see if it was matched correctly, to the first set of lines and see if they were matched correctly, and then to the other ones, right? But if you want to study a minimal problem, right, which is the first part that I was mentioning before, then I think that a minimal, if I understand correctly, I'm not an expert, but like, if I understand correctly, the minimal problems, the idea is that in those minimal problems, if you add or remove data, then you have an over-parameterized system or an under-parameterized system, and then you like kind of mess up the fibers in the sense that you end up either with too many options or with none option whatsoever for the reconstruction. So the minimal problems are kind of fixed if you want to estimate the cameras, but once you have estimated the cameras, you can just, I mean, it is enough to understand the image of one line, so you can check if one correspondence that you identify is actually correct or not, because you can do it one at a time. Yeah.
Okay, thank you very much. So let's see, we have 2 minutes left, so we have one more question. I see Francesca is raising her hand.
Yes, so I was, thank you for the talk. I find this topic very, very interesting. So my question is kind of related to Lucas, actually, because so then it's not, the point is not really what are you are taking the picture of, because I was already thinking about one next step, which could be like taking a picture of something with a higher dimension or something that, I don't know, curve or something like this. But you maybe have already replied to Lucas.
Well, so the reason why points and lines are like studied a lot is because in the first part of the reconstruction pipeline, when you are matching images, the algorithms are, most of the algorithms that exist right now can identify common points or common lines. So technically that is the data that you have right now.
I see.
What can happen is that, for example, in the rolling shutter cameras, in the rolling shutter cameras, you can identify that you can have curves, right? But these curves come from the movement of your camera. But what these matching algorithms are identifying are points and lines.
Okay.
So I think if as far as I know, maybe there exists, but as far as I know, the main reason to study just points and lines is because that is what the matching algorithms are detecting right now. So yeah. All
right, thank you.
Super. So let's thank Angélica one more time.
Thanks. I'm gonna stop sharing my screen.
Oh, there is another question, Lucas. Maybe
but we
if it's a quick one, maybe we can.
Oh, I see. Is it a quick question?
Yeah, I mean, I just had a quick question about the future projects that you had in mind.
Yeah.
So you've written about like computing the Grosvenor basis over here. So I'm just wondering, like, how would that help in this, like, in solving this problem in certain sense, or like, will that be like an algebraic thing to look at?
Well, always it's a nice to have an algebraic thing to do. Yeah. Of course, I'm interested in that. But Grosvenor basis, in general, so the good thing is that if you implement them, and if they are already fixed, I think that the implementation makes the algorithms a little bit faster. So, for example, right now, if you want to solve minimal problems, there are algorithms that have the Grosvenor basis implemented to solve the minimal problems. And then, yeah, I think it's a matter of efficiency, but also because it's nice. It's for us. I mean, of course, I understand the question, but you know, yeah.
All right, cool. Thank you.
All right. So then I would like to introduce our next speaker, Andrea Guidolin, and he will be speaking about metrics and stable invariants for persistent homology.
Yes.
So Andrea, the stage is yours.
Thanks. I'm screen sharing. I hope you see my screen and my cursor as well.
Yes, very well.
Okay. So thanks for joining or for staying after Angélica's presentation. I'm going to talk about metrics and stable invariants, which are a research line developed at KTH during the last few years. I'm going to explain how my current work fits into this research line. The first slide is about persistent homology. One of the main topics in topological data analysis is the study of homology-based invariants associated with data. And these invariants should have at least a few of the following desirable properties. They should be computable, stable, they should be also robust, by which in this talk I mean robustness to outliers, and they should be amenable to statistical analysis and machine learning methods. And the typical pipeline through which these invariants are obtained is the following. One starts from data, which is typically given as a collection of objects that encode some notion of distance. For example, a collection of point clouds. Then one, as a first step, converts this distance information into spatial information in the form of a filtration of simplicial complexes or a multi-filtration. Then the next step is actually a simplification of this information and is done by applying the homology functor so that one obtains a persistence module, which is a functor from 0 infinity to the R to vector spaces where this R is called the number of parameters of your persistence module. And the last step is a description or a summary of your persistence module by means of invariants. For example, here, this is a persistence module diagram, which is a complete invariant for one parameter persistence modules. So noise and metrics are central in this talk. And I'm going to illustrate here with three pictures what is noise. So we have a circle that is sampled in 3 different ways with some Gaussian noise, and in the last picture also with some uniformly distributed points in the square that contains the circle. And these are the corresponding invariants, the persistence diagrams. So the typical approach of TDA, topological data analysis, is to regard short bars or points close to the diagonal in the persistence diagrams as noise, and to consider the long bars as important features. And this point of view can be correct if one wants to, for example, recover the underlying topology of the space that is being sampled. But in some other cases, one maybe knows that space already, or it's not interested in knowing the space, and one may want instead to distinguish the 2 ways of sampling the space. And in this case, short bars definitely play a role and contain information. And in the third example here, we also see a type of noise, namely outliers or ambient noise, that does not translate to just short bars in the persistence diagram. So the message of this slide is that noise is context dependent. There's not a universal definition of noise. And what you choose to model as noise in your data determines a point of view that you choose to look at your data. Also, choosing what is modeled as noise determines a metric between persistence modules. So for example, I can decide to regard these 2 persistence modules or diagrams as being close or distant, depending on what I want to consider as noise. So we want to have a flexible definition of noise, not a definition of noise or metrics that is fixed a priori for our data. So the stabilization of invariants is a method that was developed at KTH and explained in a few publications. And the goal of this method is to use classical invariants, for example, from homological algebra, which are typically discrete invariants, to define stable invariants with respect to any fixed and chosen metrics on persistence modules. In this process, one starts with a discrete invariant, which is, for example, the rank of a persistence module, defined as the minimum number of generators of the persistence module. If, for example, the persistence module is a one-parameter persistence module, this is the number of bars in the barcode. Then one also has to choose a metric on persistence modules, and then this process of the stabilization returns a stable invariant called the stable rank, which assigns to any persistence module a real valued function called the stable rank of the persistence module X. These real valued functions are non-increasing, as we see here, because of the way they're defined. So the stable rank of X with respect to a metric D at T is defined as the minimum of the ranks of any persistence module Y, such that the distance between X and Y is less than or equal to T. And this definition tells us that the stable rank, the invariant, does not only capture something about the persistence module X, but also something about that persistence module relates to the whole space of persistence modules. And we can also observe that the barcode decomposition or structural theorems for persistence module do not intervene in this definition, even if they are convenient for computations. So why is this process called a stabilization? Well, as I've said, one starts by choosing a metric on persistence modules, and the stable invariant assigns to a persistence module a real valued function. And on this space of functions, we have familiar metrics, so like, for example, the L2 metric. This process is then called a stabilization because this assignment is a continuous function with respect to this chosen metrics. And needless to say, stability is very important in data analysis because we don't want our invariant to change uncontrollably as an effect of small changes in the data. So we have these stable ranks, which are invariants that live in a Hilbert space. And the way that they're mapped in this Hilbert space reflects some properties of the distance chosen between persistence module. The fact that they live in a Hilbert space is also very convenient because we have statistical methods and machine learning methods that we can apply. For example, we have a kernel method for persistence module for stable ranks. So, as I said, as part of the input of the stabilization process, we also have to choose a metric on persistence module. So, of course, we want to have a rich space of such metrics on persistence modules because we want to have an associated large family of stable invariants. So how do we define such a rich space of metrics? Well, we can use contours, which are actions of the additive monoid of non-negative real numbers on the poset of non-negative real numbers that respect the orders. And such an example of such a metric is the standard contour, which is just taking the sum. But of course, we want to have more contours because for any contour, there is an associated metric on persistence module that can be explicitly defined, even if I'm not giving the definition here. So how do we define a rich space of contours that we can use to produce metrics? We can use densities, which are strictly positive functions, and define the action on A by epsilon simply as the unique real number such that the integral of the density f from A to this number equals epsilon. And of course, this gives a contour, and it's very convenient because it's easy to produce density. They're just strictly positive functions. So in summary, we are able to produce lots of densities, and each density leads to a contour, which leads to a metric on persistence modules. And we want to use these metrics to stabilize the invariants and produce stable ranks. And this use of a large family of stable ranks was illustrated in this article by Jens Agerberg, Ryan Ramanujan, Martina Scolamiero, and Wojciech Hachulski, where one of the tasks illustrated in the article was the classification of point clouds generated from 4 plane figures. The figures are a circle, a rectangle, a triangle, and a path. Each of these plane figures was sampled 500 times with some Gaussian noise to produce some point clouds. And the task was, of course, to correctly classify these point clouds. If one uses standard stable ranks, the accuracy is already pretty good. It's 88%. And we can see in this figure the average stable ranks over each class that reveal that the classes are pretty distinct, except for the triangle and the rectangle, which are not so distinct. So to improve this classification, what was done in the article was generating 100 random densities as piecewise constant functions, and considering the associated metrics and choosing an optimal density for the classification via a cross-validation procedure. And we can see visually that the average stable ranks, according to the metric associated with this optimal density, already have a slightly different shape, and they're able to distinguish better between the 4 classes. And this reflects in improved classification accuracy that increases to 95%. So in the same article, another good property of stable ranks was illustrated, namely the fact that a subsampling procedure can be used to denoise the data in presence of outliers. So if the original point clouds are perturbed by adding 30% of uniformly distributed points in the squares, we see that the stable ranks are completely disrupted. They overlap generally. So by distinguishing the 4 plane figures and correctly classify them, what we can do is for each point cloud, we subsample the point cloud 50 times with 20% of the points, and we consider average stable ranks instead of just one stable rank for each point cloud. And with this procedure, we see that the stable ranks are again pretty much distinct, and the classification accuracy is again very good, 86%. So yeah, in this last part of the talk, I will present some ongoing work with Jens Agerberg, Martina Scolamiero, and Isaac Ren, which is related to this stabilization procedure for invariants and the study of metrics on persistence modules. The first thing that one can observe is that contours, which lead to metrics on persistence modules, correspond just to a particular type of noise systems, and I will introduce noise systems in just a minute. It's important to know that each noise system also leads to a metric on persistence module, so we will use this fact. And a noise system is a parameterized family, S, denoted by S, of subclasses S epsilon of persistence modules that satisfy certain conditions. And in particular, one condition is on short exact sequences of persistence modules. So intuitively, we regard the persistence modules in each class indexed by epsilon as noise of size epsilon. So now we can consider a one parameter persistence module X, which of course has a bar decomposition. And we can choose a real number P greater than or equal to 1. And we define the P norm of this persistence module by taking the P root of the sum of the lengths of the bars raised to the power of P. Okay, this defines the P norm of a persistence module, and this definition was given by Primož Skraba and Kate Turner in their paper about Wasserstein distances. So they also proposed an algebraic definition of Wasserstein distance between persistence module, but we observed that this definition can be easily recast in the framework of persistence, of noise systems. And we did that by defining noise systems as P, where each class of persistence module SP with index epsilon is defined as the set of all persistence modules such that the P norm is less than or equal to epsilon. And of course, we had to prove that this actually defines a noise system. So we asked ourselves if this is related to contours. Well, we know that contours bijectively correspond to so-called simple noise systems, which are closed under direct sum, while we observe that these noise systems that we define are not closed under direct sum. So what we define here is fundamentally different from noise systems associated to contours. But there is a nice interaction of these definitions with contours. Namely, we can define the P norm of a persistence module with respect to a contour by taking the P root not of the sum of lengths of the bars, but of the sum of lifetimes of the bars, where the lifetime of a bar is defined in terms of the contour, and it's the amount by which we have to act on the birth time of the bar to reach the death time of the bar. So what we gain is that now associated with these noise systems, for each P and Q real number greater than or equal to 1, we have metrics parameterized by this P and Q. The algebraic Wasserstein metrics on persistence modules. And these metrics are defined in terms of this P norm of the kernels and cokernels of any pair of morphisms from any persistence module Z to the fixed persistence modules X and Y. And we have an algorithm to compute the stable ranks with respect to this family of algebraic Wasserstein metrics. So for example, if X is a persistence module with this barcode, this picture represents its stable rank, which is again this real valued function. And here, in this case, P equals Q equals 1. So of course, we are interested in studying the dependence of these stable ranks on the parameters P and Q. And we've done this on some real world data that is the data studied in this article by Paul Bendich and co-authors on persistent homology analysis of brain artery trees. So the data set in this work is a collection of 98 brain artery trees that are objects like this one that live in R3. And they are for 98 individuals of different age. And one of the questions addressed in the paper is whether the structure of brain arteries correlates with age. The authors find out that this was actually the case by considering a certain filtration of these geometric objects and considering the H0 persistence diagrams to compare these brain artery trees. The way this comparison was carried out was by vectorizing these persistence diagrams by selecting the 100 largest bar lengths of the diagrams. So these diagrams are mapped to a 100-dimensional vector space, and then PCA is done, and it was found out that the first principal component significantly correlates with age, and this is also visible from this picture. So what we did was we reproduced this approach using stable ranks instead, and these stable ranks were stabilized with respect to these algebraic Wasserstein distances with Q equals 1 and different values of P. We observed the same significant correlation between the first principal component and age, but interestingly, we noticed that this correlation is much more significant for low values of P than for high values of P. And we think this may be connected to an observation made in the original paper about the fact that long bars in the barcode or highly persistent features of the data are not the one that carry relevant information here for correlating shape of brain artery trees to age. And this is why they chose to select 100 bars because the relevant information was contained also in medium length bars. And we think this represents the same phenomenon because for low values of P, the algebraic Wasserstein metrics give more relevance to a high number of short bars, which are usually overlooked applying metrics with high values of P, which give more relevance to highly persistent features. So I think I've arrived to just read you the conclusions of this talk. So noise is actually a choice, it's context dependent. And we want to be able to vary metrics on persistence module to be able to vary the definition of noise that we apply. Stable ranks associated with metrics given by contours and density provide a very flexible pipeline for TDA, and I've illustrated this, for example, in a supervised learning context. And also, finally, Wasserstein distances or metrics can be defined algebraically and used for stabilization of invariants. Yes, thank you.
Thank you, Andrea. So everybody, let's give Andrea an applause. It's a very nice talk. Thank you. And do we have any questions from the audience? So maybe I have a question. So I was thinking about this noise. As you say, it is context dependent, right? And somewhere in the middle, when you experimented, you noticed that trying like if you you chose different kinds of metrics on this space of persistent modules, and by like somehow looking at many different choices and then averaging gave you a good way to gave you better results. Is that correct? Did I understand this?
That procedure was to eliminate a different type of noise that is not possible to eliminate directly from just a given persistence module. That noise regards the original data rather than the persistence module. Yes.
Yeah, exactly.
So I'm not showing here persistence diagrams for this 4 point clouds, but the idea is that this subsampling procedure with respect to a fixed metric, we are not varying the metric here, is able to on average to correctly capture the patterns of clusters and holes that are typically detected by persistent homology, but in this case are completely disrupted by the presence of outliers.
Okay, thank you. We have a question from Francesca, and we have another question in the chat. Let's see. So Rolando asks, how would the behavior be? How would the behavior of stable rank in high-dimensional homology groups be?
Yes, we have not largely investigated that, but we expect more or less to be similar to the one in low dimension. The bottleneck here to explore this is computational. But stable ranks are non-increasing functions that capture patterns in the data. And it is possible that for some specific data, high-dimensional homology is able to be more informative than low-dimensional homology. But yeah, as I said, typically the bottleneck is computational for high-dimensional homology.
Okay. Let's see. We have time for a few more questions. So I saw Francesca raised her hand.
Yeah, it's a very, very quick one, probably. Was it just natural to take the Wasserstein distance because it gives a nice norm for persistence module, or there were just other candidates?
It was nice. To me, there are at least 2 reasons to consider this. The first one is that, as I said, this gives noise systems which are fundamentally different from contours. So we are enriching the space of metrics that we can consider and use in analysis. And the second reason is that there is just 1 or 2 parameters that is involved in the definition of Wasserstein distances, this P and Q. And this is good because these 2 parameters control, in my intuition, the scale at which you want to look and to find a balance between short bars and long bars in your data. It's just controlled by 1 parameter. It may be convenient to adjust that parameter on the data to understand and to exploit the correct balance between highly persistent features and medium or low persistent features.
Thank you. Very nice.
Right. Maybe also a short question from Wojtek.
Yeah, this is more a comment to the previous question, not to Francesca, to the before Francesca. So from the experiments that we've been doing, is that if you leave the same
Oh yes, sir.
This one. So the subsampling technique is very effective in denoising. However, for H0, you know, if you subsample, you might ask, how many times do I need to subsample? Very often for H0, you need to maybe do 100, you know, a few hundred times. For H1, to get to lower deviation, you have to do like another order, a few thousand times. For H2, you have to subsample even more, okay? So this limit, I mean, law of large number, I mean, we know it will converge to some expectations, but higher homology, you know, this convergence is slower, okay? And it's like, it seems like, you know, really on the order of you know, slower, okay? Just a comment, okay?
Thank you. Great. So let's thank Andrea one more time.
Thank you very much.
Yeah, thank you. Right, and then I would like to introduce our next speaker. So, Alex, are you here?
Yes, I'm trying to share my screen now.
Yes, go ahead.
Okay.
So let me introduce you. So, Alex Markham, his title is Unconditional Equivalence of Causal Model and its Representation with Undirected Graph. So please go ahead, Alex.
Okay, y'all can see my slides?
Yes,
Okay,
and your
great. Yeah. Okay. Yeah. So hi everyone. I'm Alex. I'm a postdoc in the group there, and yeah, today I'll talk about unconditional equivalence of causal models and its representation with undirected graphs. So it's based on a project. It's joint work with Denai and Pratik and Liam, all here at KTH, and we just recently put a paper up on arXiv that you can see there on the bottom called Causal Structure Learning with Greedy Unconditional Equivalence Search. So the things I'll talk about in this talk are kind of come from working on this paper, but the actual ideas in the paper aren't what I'm presenting so much, but it's kind of related. So yeah. Okay, so to start with, just a quick outline. I will, so that when I'm talking about undirected graphs and causality and stuff, you have some kind of context. I'll start with an overview of causal DAGs, so directed acyclic graphs. And then in causal DAGs, there's a sort of important or common notion of Markov equivalence. And then that'll kind of give the background so that I can talk about the actual research we've been doing, which is on a different kind of equivalence called unconditional equivalence, and how that's related to undirected graphs. Okay, so to start, very basically, a causal model consists of a joint distribution over a set of random variables. So this is just exactly very simple, like it sounds, and it's just in the very familiar language of probability theory. But along with that, we have a set of post-intervention distributions for possible interventions. And so this is what really makes it a causal model as opposed to just a probabilistic model. A post-intervention distribution, it's something like you kind of extend the language of probability theory by adding in what's called like the do calculus or the intervention calculus. And it allows you to kind of formalize not just like a conditional probability, you know, A given B, but more sort of interactive and especially related to causality, which is like the probability of A given that we intervened, we did something, we changed the value or set the value of B. Yeah, and so DAGs, directed acyclic graphs, give an intuitive representation of causal structure and causal models. In particular, there's this idea called like deseparation, and it encodes, so it's a graphical thing in DAGs, and it encodes conditional independence statements in the probability distributions that the DAGs represent. And so if you give me like a joint distribution over a set of random variables, and if it's kind of, if some assumptions go right, then you can draw up a DAG where all the deseparation statements of that DAG correspond to the CI statements in the distribution. And then furthermore, the directed arrows, even beyond helping with deseparation, they kind of further encode which conditional distributions are affected by which interventions. And intuitively in a DAG, if you have like A arrows B, it just means that A causes B. So these are why we're interested in DAGs to begin with. And then what I'll get to later in the talk is how we kind of relate DAGs to certain kinds of undirected graphs. And so you can kind of trace it like DAGs represent causality in this way. And then we're going to talk about how these DAGs correspond to undirected graphs. And so you can kind of go back and see how the sorts of questions and sort of answers we come up with related to undirected graphs have causal interpretations for learning causal structures. Okay, so now to talk a bit about Markov equivalence for DAGs. So interventional data, so this is like if you do some experiment or kind of the classic like trial where, you know, you randomly pick some participants to give some kind of drug or treatment and then randomly pick some other ones to give like a placebo. So these kind of interventional or experimental studies, this data, it's relatively more scarce than just observational data. And so a kind of common question is, to what extent can we learn causal structure from purely observational data? And so when trying to answer this question, different DAGs, so like different causal structures, can represent the same set of observational distributions based on only the conditional independent statements. And so kind of without doing experiments or interventions, you can't learn the full causal model, but you can learn up to this observational equivalence, or also called Markov equivalence. Graphically, two DAGs are Markov equivalents when they entail the same d-separation statements. And then something that's been proven is that two DAGs entail the same d-separation statements when they have the same undirected skeletons and V-structures. So an undirected skeleton is just you give me DAG and I just replace all the directed edges with undirected edges. That's the skeleton. And then a V-structure is any induced subgraph of this form down here, where you've got two nodes, I and J, that aren't adjacent, there's no edge between them, but they have a common child, K. So this is a V-structure. And yeah, so if you have two DAGs and they have the same skeletons and all the same V-structures, then they entail the same d-separation statements and they're Markov equivalent. And based on this idea of the skeletons and the V-structures, you can make a mixed graph, which is a kind of unique representative of each Markov equivalence class of DAGs. So you just take the skeleton, the undirected one, and go in and direct all the edges that are part of the V-structures, and that gives you a representative of the Markov equivalence class. On the past two slides, a lot of stuff we talked about, it's kind of classic from when the field of like causal discovery was being made in like the 90s. So a lot of the ideas originally from papers then, but since then there's kind of two good overview or reference books if you're interested. So one, you can see at the bottom here, is by Andrea Guidolin, it's just called Causality. And then the other is by Spiritis, Gleamore, and Shines, called Causation Prediction Search, in case you want a reference to kind of dig into the details of some of the stuff I've been talking about. Okay, so now we can talk about actual research now that you've got a bit of kind of context for it. And so we'll start by defining the unconditional dependence graph. So if you give me a DAG G and I can construct an undirected graph, so it's over the same set of vertices, and just we look at two nodes in the DAG, and if they're D-connected in G, then I just put an undirected edge between them in this undirected graph I'm making. So this importantly is, in some cases, this is different from the undirected skeleton. So you can have nodes that are D-connected in a DAG, but which aren't adjacent. There's no direct edge between them, but there's kind of a causal path between them. But in this undirected graph, this unconditional dependence graph, any nodes where there's this like causal path between them just have a direct undirected edge between them. So using this idea of unconditional equivalence, or of the unconditional dependence graph, we can define unconditional equivalence. And so two DAGs are unconditionally equivalent when their undirected dependence graphs are the same. And so one question is, which undirected graphs represent like non-empty equivalence classes of DAGs? So is there some way of characterizing, which undirected graphs correspond to these equivalence classes of DAGs? Because not all of them do, but so for example, what about this undirected graph here? Maybe take a moment and try to think about it. Is there some way we can make a directed graph, a DAG, that has deseparation statements that correspond exactly to this? And so I maybe didn't define deseparation because it's pretty complicated, but for this simple example, you can just think about two nodes are deseparated if they have this induced subgraph I talked about in the slide before, where there's this V structure between them. And so here, if you wanted to figure out if a DAG over these 4 nodes is in this class, you just have to think about, is there a way of directing these edges that is a DAG and that we don't put V structures between, that we only put V structures between things that that don't have edges between them. So for example, if you look at this orientation of all the edges, it doesn't quite work. So we can't remove any edges because here in this undirected graph, 1 and 2, and 2 and 3, and 3 and 4, these are all, there's kind of no other paths. So there's no way to get from 1 to 3, from 1 to 2, except for that direct edge. And so all of these edges are kind of necessary in any DAG in this class. And so all we can do is direct them. And so now if we try to direct them, though, for example, here, we maybe direct from 1 to 2 and from 3 to 2, but then that creates this, and then we can direct maybe from 4 to 3. But then now 4 and 2, you see this path here, it's not that V structure that we talked about earlier. So actually in the undirected graph corresponding to this DAG we've drawn, 4 and 2 would need an undirected edge. And I picked this DAG in particular because kind of, maybe we could reverse the edge and make it go from 3 to 4. But still then 2 and 4 would be deconnected. And so their undirected graph wouldn't look like the one we're after. It would rather look like where there's an edge between 2 and 4. And so the point is, this undirected graph here is an example of one of the undirected graphs that doesn't correspond to any DAGs. And so we're after some way of characterizing this more generally. And so we came up with this theorem to actually characterize it and answer that question. So the set of DAGs corresponding to an undirected graph U is non-empty. Oh, that should say if and only if, not if and on slide. So if and only if alpha of U, which is the independence number, equals delta of U, which is the intersection number. So I'll just sketch the proof now, and the first thing I'll do is kind of explain, if you're not aware, what the independence number and intersection number are. So in an undirected graph, you can always find this thing called the maximum independent set. And so it's just a set of nodes, none of which are adjacent to each other. And it's sort of the biggest such set you can find in a graph. And so just the cardinality of this set, M, is the independence number for that graph. Okay. And then for the intersection number, it's based on this thing called a minimal edge click cover. So a minimal edge click cover is just a collection of cliques that kind of contain all the edges. Their union contains all edges in the graph. And then it's minimum if there's no smaller collection of cliques that contains all edges. And the cardinality of this set is the intersection number. So one thing to notice is just that there's a natural injection from between these sets. So first thing to notice is that of course, every node in the graph is contained in some clique in the minimum edge click cover. But more specifically, these nodes in this maximum independent set, they're all contained in different cliques in the minimum edge click cover. So if they were in the same clique, of course, that would mean there's an edge between them, and so they wouldn't be a part of an independent set. And so another thing to note here is that the me make sure I get it right. The independence number. So the intersection number is always greater than or equal to the intersection number. Maybe I misspoke, so I'll say it again. The intersection number is always greater than or equal to the independence number for any graph. And that's also related to how you have this natural injection. So you give me a node in the independent set, and I can sort of find the unique clique it corresponds to in the minimum edge clique cover. But maybe there's some cliques in the minimum edge clique cover that are empty. And so, yeah, if we assume that the intersection number and the independence number are equal, then this function, it's not only injective, it's also surjective. And so we have this like bijection. And so every clique in the minimum edge clique cover has one node from a maximum independent set. Yeah, and every node in the maximum independent set is in one of the cliques. And so we can use this bijection to construct a DAG. We do that by, we take the node that's in the maximum independent set, and then we put an arc from it to all other vertices that are, all other nodes that are in the same clique in the minimum edge clique cover. So this is guaranteed to give us a DAG. And furthermore, it's guaranteed to give us a DAG whose unconditional dependence graph is exactly the U with these maximum independent set and this minimum edge clique cover. So what this shows is that if the intersection and dependence number are equal, then that undirected graph represents some DAGs. And so now we just need to show the other direction. And yeah, so this is the kind of hard part of the proof. This is the main reason it's a sketch, is because this takes a lot more details. But the simple short version of it is just that if these numbers aren't equal, then we can use the kind of non-surjectiveness of F. We can use the fact that there exist cliques in the minimum edge clique cover with no independent vertices in them to prove that the clique structure of U can't possibly correspond to the unconditional deseparation statements of any DAG. Okay, and then two corollaries of this. So the first one is that there's a polynomial. So in general, to calculate the intersection number, to find one of these minimal edge clique covers, or to calculate the independence number, find the maximum independent set, it's an NP hard problem. But when they're equal, so we can actually in polynomial time decide if these numbers are equal, and then if they're equal, we can compute them in polynomial time. So that's an interesting kind of result of this theorem. And then another one is that for given n, so given like number of nodes, there's a bijection between undirected graphs over n nodes, such that the independence and intersection number are equal. And so there's a bijection between that and then just the minimal covers of n objects. And so this bijection means that the sequence where you look at the number of unconditional equivalence classes of DAGs on n nodes is just this sequence we have here, this OEI sequence. Okay, so now with that, I'll kind of, that was kind of the mathematical view of the things, and now I can spend the last couple minutes describing how sort of the causal interpretation of these, or the significance for this in terms of causal structure learning. So one thing to kind of emphasize is that, maybe if it's too quick, way back in the beginning, when we were talking about these Markov equivalence classes and learning up to Markov equivalence class, this is based on conditional independent statements. And so one way of learning this Markov equivalence class is just that you do kind of all the possible conditional independence tests for your data. So you look at every pair of variables, and then you test conditioning on like every possible combination of the other variables. So the point of saying it like that is to emphasize that it's a lot of tests. So that's kind of the constraint-based or like test approach to it. Another way you can do it is instead think about like the space of all Markov equivalence classes over a set of nodes. And then you can sort of, in a smart way, search this space, kind of moving from one Markov equivalence class to another using the scoring function. And you can do that until you find the optimal one. But still, it's the space of all Markov equivalence classes over that many nodes. So in both of these approaches, the usual way of finding Markov equivalence class, you either have to do a lot of these tests, or you have to search this big space, or some combination of the two. But with the sort of significance of this unconditional equivalence class is it's based only on unconditional deseparation. And so you can actually estimate this U graph, this unconditional dependence graph from data with just like n choose 2 tests. So you just have to look at every pair of variables, and you don't have to do all the long conditioning sets. So you can use that to get U. And then once you have U, you know, like now you don't have to look at the entire space of Markov equivalence classes. Because the unconditional equivalence class, it's a partition coarsening of Markov equivalence classes. And so it kind of nicely divides the space of Markov equivalence classes up in a way that if you know your data is generated by something with a certain U graph, now your search space to find the right Markov equivalence class is greatly reduced. And so the archive paper I had at the beginning here, we use that that kind of fact to propose a causal structure learning algorithm based on this. And now I'll go back to this slide and to say a little bit more. I've got a few minutes. So then some other kind of causal implications or interpretations of this. So for the first correlator here, so one of the things I said in the beginning was that, you know, not all data sets necessarily come from sort of a causal structure that can be represented by a DAG. Sometimes you maybe didn't observe all the variables you need to, or maybe, yeah. And so what this polynomial time algorithm to decide if U contains any DAGs or not means is that in polynomial time, we can decide whether a given data set kind of has a causal structure generated by a DAG or not, which is maybe an interesting thing to do because it can be expensive to learn like a full causal model. And so this can be a nice way to decide early, well, can we even actually learn a causal DAG for this data or not? Another result of this is that because we can compute the independence number, we can, basically the way we do this also gives us a way for identifying which nodes are sort of the causal sources. So these have to be the source nodes in any DAG in that class. And so you can use this to also quickly figure out which nodes are the causal sources, which is maybe interesting. And then for the second correlator down here, one of our kind of hope in starting to explore this, we're just starting, but the idea is maybe that this makes more clear the sort of combinatorial structure of unconditional equivalence classes. And so maybe we can find like a Markov basis for these, and we can move between them in a nice way so that we can, instead of using this sort of constraint-based way where we just do independence tests to estimate U, maybe we can kind of do it in a nicer way using like a score-based approach. Yep, okay, so thanks for listening. And now any questions?
All right, so thank you very much, Alex. Thank you. Do we have any questions from the audience? So Francesca has a question.
Yeah, I do. Is there a class of graphs having this property of having numbers, intersection and independence number equal? Like, I don't know, complete graphs always have it, or they don't, or?
Yeah, so complete graphs always do have it. But other than that, I mean, I guess maybe I looked at some, but generally I haven't found any that kind of some description that sort of perfectly corresponds to these. As far as I can tell, this is sort of defines a sort of unique class of graphs. which includes complete graphs and some other special ones, but yeah.
I see. All right, thanks.
Then I also have a question. Could you say a few words about like possible future work or open questions, similar open questions? Because again, AlToGeLiS is about trying to start communication and talk about new problems. So do you have any ideas for future work?
Yeah, so that's what I was trying to hint at in the end here when I was talking about sort of the possible causal interpretations of these corollaries. So in the archive paper I mentioned at the beginning, we kind of already have this hybrid causal structure learning algorithm where we first do independence tests, like unconditional independence tests to estimate U. And then, so that's the kind of constraint-based approach. And then once we have U, we used a score-based method to find the right Markov equivalence class for the data. And so then it's hybrid because we've got a little bit of constraint, a little bit of score-based. But generally, constraint-based tests kind of, if you just get one thing wrong, it can mess up sort of the rest of the process. And so instead of, and then things also tend to go wrong. Like there's a reasonable, if you, over just like 5 nodes or something, there's already a reasonably high probability of getting at least one of the tests wrong. And so it would be nicer if instead we could do some kind of score-based way of moving between these undirected graphs. And so that's why we're hoping here with this bottom corollary that it helps us sort of come up with some, yeah, like a Markov basis for moving between these undirected graphs. And then we could do like, yeah, so that would kind of get rid of the constraint-based approach and hopefully make a more sort of robust causal structure learning algorithm. And also for future work. So here I talked about how it's unconditional equivalence classes over DAGs, but it's also actually an unconditional equivalence class. Like you can also define it over broader types of mixed graphs. So in causality, there are these things called ancestral graphs, which have 3 or 5, I think 4 edge types instead of just 2, like undirected and directed. And these undirected graphs also form an equivalence class over these. And so there could be lots of work for that, kind of exploring the causal interpretation in this more general sense instead of restricting yourself to tags.
It's very interesting. Thank you. All right. Do we have any further questions? Otherwise, let's thank Alex once again. All right. And